Today's notes are on the fundamental theorem of algebra. Doesn't that sound exciting? The fundamental theorem of algebra. This is section 2-5 in your textbook. Now, what the fundamental theorem of algebra is, what it tells us is that all polynomial functions, these things we've been talking about lately, all polynomial functions have at least one zero. So it could be a real zero, it could be imaginary. Usually they have many more than one, but all polynomial functions have at least one zero. And then this linear factorization theorem tells us that these polynomial functions don't just have at least one, they have exactly n factors, where n is the degree. So let's get that down here. Let's see here. There we go. All polynomial of degree n have exactly n factors. Excuse me. So if you have a function such as f of x equals x to the fifth plus et cetera, et cetera, et cetera, you know that that will have exactly 5 factors. Okay, last idea. Complex zeros occur in conjugate pairs. So if you end up with a complex zero such as 5 plus 2i, you will always have a zero that is its conjugate, 5 minus 2i. So you'll always have pairs of complex zeros. Now this goes back to something we learned about a couple units, a couple lessons ago with Descartes' theorem, his number of possible signs. I said that there could be 5 zeros or a value less than that by an even number, so 5 or 3 or 1. That's because if you have any complex zeros, there's always going to be 2 of them, or maybe 4 of them, or maybe 6 of them. Okay, so there's our big ideas before we start. Let's jump into examples. First example, we need to factor this and find all of the zeros. Now we know there are 3 possible zeros. We know that based on sign changes, there's 1 change, 2 changes, there's 3 positive possible zeros. There aren't going to be any negative ones. Now when I say 3 positive possible, it could be 3 or less than that by an even number if any of these are complex. So what we have to do first is just use a little trial and error to find a zero. So the possible zeros are the factors of this number, -2, over the factors of this number, 1. So the possible zeros are 1 or 2. It could be positive or, well, actually it can't be negative at all. So possible numbers to check are either going to be 1 or 2. Okay, so let's check 1. So if I plug 1 in here, I get 1 minus 3 plus 4 minus 2. And if I add that together, yes, that does equal 0. So that's a good sign. That means 1 is a factor. Or excuse me, 1 is a 0, which means x minus 1 is a factor. So we need to find what this other factor is. Okay, so let's use a little synthetic division. So 1 was one of the zeros. Let's write down these coefficients. We know we need to add down, multiply diagonally. I'm going to continue that process until I get a remainder of 0. That's a good sign. So x squared minus 2x plus 2 is the other factor. Now in the past, here's where we would try to factor this a little further. We'd say, hey, this must be x, and at this point for this particular problem, we'd get stuck. We cannot factor this further. So we have to use a different method here. We have to think back to what we did in the last unit. We have to use the quadratic formula. So what we're really doing here is finding where this whole thing equals 0. So to do that, I'm going to bring that quadratic formula here. It's kind of a catchy tune, isn't it? Let's plug a, b, and c into the quadratic formula. So if we do that, we get x could equal here 2 plus or minus the square root of 4 minus 4 times 2 minus 8 all over 2, which is equal to 2 plus or minus the square root of negative 4 all over 2, which is equal to 2 plus or minus 2i all over 2, or 1 plus or minus I. So that means one of the zeros is going to be 1 plus I, one of the zeros is going to be 1 minus I. So the directions say we need to factor this. So even though we have these complex zeros, we still need to factor. Here's how we do that. We say it's going to be x minus 1 plus I and x minus 1 minus I. So there's the first part of our answer. There is this polynomial completely factored. Our zeros are the numbers we could plug in here to make it equal 0. So 1 we found right away, and then 1 plus or minus I is 2 more complex numbers that work as well. Now, don't forget, make sure you give both parts of this answer. Make sure you give the factored form of the polynomial and the zeros. Often people forget this first part and jump right to the zeros. Make sure you do both. Okay, I have another example, same basic idea. So let's just think about this. 3 possible zeros. We have 1, 2, I'm thinking 3 positive zeros we're going to have here, or 1. The possible numbers are factors of 10 over factors of 1. Let's just test them. If I plug 1 in here, I get 1 minus 6 plus 13 minus 10. That does not equal 0. So let's plug something else in here. Let's plug 2 in here. 2 cubed is 8, 2 squared is 4, so that's minus 24, plus 13 times 2 minus 10. You know what? That does work. That does equal 0. So 2 is a 0, meaning x minus 2 is a factor. Now we have to use some synthetic division to find out what the other factor would be. So let's put a 2 over here. Let's bring these terms over. You might notice these problems, there's a ton of different mathematical skills involved in doing these. So if you can do these problems here, you can do anything that I can throw at you. Remainder of 0, that's a good sign. X squared minus 4x plus 5. Okay, now we want to factor this a little further. However, if we try to factor this by hand, we'll see that it is impossible. So I'm going to use the quadratic formula here. I'm not going to write it all out. We've already got it written down. We know the tune, and we know that x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, which is 4 plus or minus the square root of negative 4 over 2, which is 4 plus or minus 2i over 2. Now remember, the whole thing's divided by 2, so let's divide everything by 2, which gives me 2 plus or minus I. So I can write my factors as x minus 2 plus I and x minus 2 minus I. Zeros we can write as 2, that first one we found, and 2 plus or minus I. So there's our zeros. There's our factored form. We need both of these to answer this question. We factored and we found the zeros. Okay, let's run through as difficult an example as I could possibly give you. We want to factor and find all the zeros of this polynomial function. Look how complex this is. We are looking for 5 zeros, 5 factors. We know that, let's see here, there's 2 possible sign changes. So 2 or 0 of these could be positive, meaning 3 or 1 of these could be negative. The zeros could be factors of this number 18 divided by factors of 1. So let's just use some trial and error to find some of these. Let's try 1. If I plug 1 in here, I get 1 plus 6 plus 2 minus 27 plus 18. And guess what? That works. So plugging 1 in here works, which means x minus 1 is a factor. Now what's the other factor? Let's find out using synthetic division. Careful here. Notice there's no x to the 4th term, so I'm going to have to put a 0 in that spot. All right. Adding down, multiplying diagonally, continuing that process gives us a remainder of 0. Good sign. But it tells me that x to the fourth plus x to the third plus 7x squared plus 9x minus 18 is also a factor of this polynomial. And we want to break that down a little further. So let's test some other numbers. Now, we already tested 1, but it doesn't mean 1 won't work again. So let's plug 1 in here again. That gives me 1 plus 7 plus 9 minus 18. Guess what? That equals 0, so 1 works again. Meaning, when we break this down, we're going to have x minus 1, another x minus 1 times something. Now, check this out. I'm just going to use what I had before and go through the same process of synthetic division. And again, we get a remainder of 0. Good sign. So x cubed plus 2x squared plus 9x plus 18. All right, do you think 1 will work again? Well, if you remember what we started with, we said we could have 2 positive. We already have our 2 positive zeros. And in fact, if you plug 1 in here, it won't work. Let's try negative 1. That'll give me negative 1 plus 2 minus 9. No, negative 1 does not appear to work. I'm not going to try any more positive numbers, but let's try negative 2. That gives me negative 8. Negative 2 squared is 4 plus 8. Minus 18 plus 18. Negative 2 works. Okay, so that means this is going to be my original factors. X plus 2 times something else. So let's try this negative 2 out here. Let's use synthetic division once again. Remainder of 0, that's a good sign, so we're left with x squared plus 0x plus 9. And if you try to factor that, you'll find that it's impossible. So I'm going to now jump to that quadratic formula. So I know x equals negative b. Hey, there's no b term, so that's like 0 plus or minus square root of b squared minus 4 times a, which is 1, times c, which is 9, all over 2a, which equals plus or minus 6i over 2, which is plus or minus 3i. So now we've got this thing factored completely. X minus 1 times another x minus 1 times x plus 2 times x minus 3i times x plus 3i. And our zeros are the numbers we could plug in there to make it equal 0, such as 1. Now you don't have to write 1 again. We already got it once. Negative 2 and plus or minus 3i. And that, ladies and gentlemen, is as difficult a problem as I could possibly give you. So if you can do that, you can do anything. All right, now that doesn't mean we're done for the day, because I have one last example for us to look at, and I'm asking you to go backwards here. Now I'm saying, here's the zeros. We want to find a polynomial function. Now I'm just going to skip back here. If these were the zeros, we could write them as factors. If we have the factors, we can multiply them to write it as a function. So that's what we want to try to do in this problem. Now here's a big warning for you. Way back at the beginning of these notes, we wrote down complex zeros always occur in conjugate pairs. So for example, on this problem, since 3i was a 0, so was minus 3i. Here, since 2 plus I was a 0, so is 2 minus I. Here, since 2 minus 3i is a 0, so is, oh, why did I write that? So is 2 plus 3i. So we have 3 zeros. So our function is going to be like y equals x to the third power. Here's going to be our factors. X minus 1 is one of the factors. X minus 2 minus 3i is another factor. And x minus 2 plus 3i is another factor. Okay, so we need to multiply all these together. Here's what I would suggest. Before you do that, let's distribute these minus signs and write this as x minus 2 plus 3i and x minus 2 minus 3i. And don't forget x minus 1. Now the order you multiply these in really doesn't matter, but I would strongly suggest that we multiply these trinomials together first. Because if you do that, guaranteed every time, the I terms will cancel out. You'll have some positive I values, some negative I values, they'll be gone. Okay, so let's do that. So multiplying every term of the first by every term of the second gives us x squared minus 2x minus 3ix. That's the x times everything. Now minus 2 times everything. Minus 2x plus 4 plus 6i. Now the 3i times everything, so we get plus 3ix minus 6i minus 9i squared. And you should see at this point some terms that will add up to give us zeros. So for example, these two terms, they're gone. These two terms, they're gone. In fact, those imaginary terms will always be gone. In fact, look at this last one. Minus 9i squared. I squared is negative 1, right? So this is the same as plus 9. Okay, let's combine our like terms then. We have x squared minus 4x plus 13. So that big mess simplified to this trinomial. We still need to multiply it by x minus 1, but I think you'll agree this is much simpler than what we had before with those imaginary terms. So now if we use our distributive property, we should be set. If we do that, we'll get x to the third minus 4x squared plus 13x minus 1x squared plus 4x minus 13. And if we combine like terms, there's a polynomial function, so I'm going to write it in function notation. F of x equals x cubed minus 5x squared plus 17x minus 13. Now if you ever want to check this, you could factor and use synthetic division, use the quadratic formula. You'd get these zeros. That's a lot of work. We'll just trust our work for right now, but if you needed to check, you could. Okay, that wraps up the notes for this unit. Take a look at this assignment on page 144. When you're done with this, you can move on to the next section, which would be 2-8. Skipping a couple sections here. Move on to 2-8 when you're done with this section.